All right, I decided to do one more. Couldn't stop me. It's just so exciting, You can't help from wanting to do more. So this is 2017, number 3, I think. Pretty sure it's number 3. So we got a little example circuit here. Solenoid. Whoops, too far. Solenoid, power supply, resistor, multimeter. When studying Ampere's law, students collect data on the magnetic field of two different solenoids in order to determine the magnetic permeability of free space, which is the constant mu. Solenoids are created by wrapping wire around a hollow plastic tube. Solenoids of length L and turns N of wire will be connected in series to a power supply, and resistor. The multimeter will be used as an ammeter to measure the magnitude of the current through the solenoids. The main components for the setup are shown above. On the figure, draw a wire connections between the solenoid, power supply, and resistor and multimeter that will complete the circuit and allow students to measure the magnetic magnitude of the current through the solenoid. So let's connect these components here. And it's actually pretty straightforward. We just need everything to be connected in series with each other, right? As long as everything's connected in series, we'll be able to have normal current flow through the circuit, right? If all of a sudden we connect the solenoid and the resistor in parallel, or the solenoid and the multimeter in parallel, we won't be able to measure the current, right? We want the current through the solenoid. And in order to measure current, we need the thing that's going to measure current to be in series. That's the only way we can for sure know that we're getting the same series or the same current through the solenoid and being measured by the multimeter. So I'm just going to connect everything in series, one after the other. There we go. That's all we got to do. Connect everything in series. So we have a chain where the multimeter is going to be measuring the correct current. Power supply is allowed to flow through the entire circuit or power the entire circuit. We're good to go. Using the connections you made, what will be the direction of the magnetic field inside the solenoid? So depending on which way you connected your circuit, you could have two different answers for this one, but I assume most people would connect it the way I connected. And as you can see, the wire goes up over the top and then around from the bottom, right? That's what this first little part is doing right here, right? It's going right up over the top. So up over the top, around the bottom, that's current going this way. My thumb is pointing to the left, which would be to the left. There we go. Easy peasy. And we don't even have to justify. How nice. Rectangle shown below represents the solenoid. Loops of wire not shown. Points A, B, and C are along the central axis. Point B at the middle of the solenoid. Point D is directly above point B. From the choices below, select the point where you would place a magnetic field probe to best measure the strength of the magnetic field of the solenoid in order to determine the magnetic permeability of free space. I think it should be pretty straightforward to you that B is going to be the correct answer, but let's talk about why and justify why B is correct and the rest are not. First, if we're talking about an ideal solenoid, D is not going to have any magnetic field, right? D is outside the solenoid. Its magnetic field isn't even going to be relevant to the solenoid that we're measuring. C is also outside the solenoid, so we'll get rid of that one right away. So D and C are outside, which means they're going to have a much weaker field, if not zero, right? C is not going to be zero. D might be zero. So we get a much weaker B for those ones. And we can't even be 100% sure about the direction for those. But they're just not nearly as good. And then if we look at A, because A isn't in the direct middle, if we're not talking about an ideal solenoid, which we're not because we're talking about an actual solenoid, and actual solenoids will never be ideal. As soon as we leave the very center, and the farther away that we get from the center, we start to get to these end disturbances, right? So maybe the field for this solenoid looks kind of like this, right? and it's nice and parallel and uniform in the middle. But when we get to A, you can see kind of how the ends are distorting. There's not going to be as uniform a magnetic field at the ends as there is in the middle. So B is going to be more uniform than A. Because of possible end distortions. Sorry, it's late. Not that I can spell anyways, but distortions. I just needed an S. Why did I start writing shuns again? Whatever. So B is going to be the best choice there. Figures below show two different solenoids that will be connected. So the two solenoids that they're using are shown there. Solenoid 1 has length L equals 25 and 100. Solenoid 2 has length L5 and 5. Graph of the magnitude of the magnetic field as a function of Ni over L is shown below. The best fit line is shown for solenoid 1 and dashed for solenoid 2. So we have visual representations of the solenoids. We also have graphical lines of solenoids, best fit lines for the solenoids. Which solenoid's best fit line would give the best results for determining the value for magnetic field? So there are a couple possible ways that we could talk about this. We could talk about looking at the actual shape of the solenoid, right? Solenoid number 1 is closer to an ideal solenoid. It's longer and it's going to have more turns per unit length, right? So just physically looking at the solenoid, solenoid number 1 is going to be better because it's closer to an ideal solenoid. Right, it has a bigger length, right? So it has more length and it has more turns per length, which are both good things when we're trying to work towards approximating an ideal solenoid. The second way that you can do it, which I didn't even think of this as a way, is actually calculate the slopes for each of these and then see which one is closer to the ideal solenoid, right? So if you don't feel like explaining it physically, you could actually just calculate the slope for both and then state which one is a better choice for an ideal solenoid. So whichever way you want to do it, they both work. I did it using kind of the geometry of the solenoid to explain why it would be better. Use the slope of the best fit line for the solenoid chosen in part B to calculate the magnetic permeability of free space. So I chose solenoid 1, so I would use this solenoid to calculate the permeability of free space. We're looking at the magnetic field of a solenoid, which is mu naught Ni over L, sorry. Which is essentially what we have plotted on the, excuse me, x-axis here, right? Ni over L. So we have this plotted on the x-axis. We have this plotted on the y-axis, which means whatever we calculate for our slope will be the equivalent of mu. So I did solenoid 1, so I just have to calculate the slope of 1. I used 72, which it looks like is this point, right? That would be 64, 68, 72, and that would be 9.6. So I use the point 72, 9.6, and the point 2844. 2844 is this point right here. So 28 and 4.4. And then we just calculate the slope. So rise over run. So 9.6 minus 4.4, that's times 10 to the negative fifth, divided by 72 minus 28. And we end up with, I didn't actually do the calculation all the way out. That's embarrassing. 5.2 times 10 to the negative fifth divided by minus 20, quick math. I got 1.2 times 10 to the negative sixth as mu. 1.2 times 10 to the negative sixth as my mu value. Mu is a fundamental constant. I believe it's unitless. Actually, we can just go up and check the units. If we have our thing here, we should have mu on here in the list of fundamental constants. Where is it? Mu is Tesla meters per amp. So there's our unit. Tesla meters per amp. Perfect. Which I should have known because that's amps per meter and that's Tesla. So I'm just stupid. We did that, calculate percent error for the experimental value of the magnetic permeability of free space. We determined in part C. So experimental is actual minus experimental over actual. So actual is 4 pi times 10 to the negative seventh minus 1.2 times 10 to the negative sixth divided by 4 pi times 10 to the negative seventh times 100. And we can get what that equals. So just real quick, I'll do it out. 4 pi times 10 to the negative seventh minus 1.2 times 10 to the negative sixth divided by 4 pi times 10 to the negative seventh times 100 is 4.5%. So my error is 4.5%. Not bad. Under 5%. Could be worse for sure. What reasonable physical explanation for a best fit line that does not pass through the origin? If we notice here, neither one of our lines of best fit pass through the origin, which is interesting because that tells us that even when current is 0, right? If you look at these, both of these are down here, right? Even when current is 0, we are getting magnetic field measurements in our solenoid. So there are a couple reasons that could happen, mostly because of external magnetic fields, right? Maybe we're doing this experiment in a way where the solenoid lines up with the magnetic field of the Earth. Right, and because we're measuring values for magnetic field that are so small, right, Tesla times 10 to the negative fifth, the magnetic field of the Earth is 2.5 times 10 to the negative fifth Tesla, right? So we're on the same factor of 10, I guess is what I'm trying to say, right? So if our magnetic field, if our solenoid is lined up with the Earth's magnetic field, we could for sure be in a situation where we would be getting disturbances or effects because of the Earth's magnetic field. So yeah, so we could definitely have those. Suppose a student connects solenoid in a closed circuit similar to circuit 1, but without the resistor. Student notices the multimeter stops functioning after the power supply is turned on. What causes the failure? So if we go back up to our first situation here, and instead of connecting this to the resistor, we just skip the resistor and go straight to the power supply, or sorry, straight to the multimeter. What's wrong with that, right? Why would the multimeter stop working? And the answer is more of a circuit question than a magnetic field question. Goes back to V equals I times R, right? If we look at current, I equals potential difference divided by R. A solenoid, particularly a solenoid that has reached steady state, right, acts as a wire with no resistance. Right, if it's made out of copper wire. What did they say? It just says wire, but innately, right, just a plain wire doesn't have a whole lot of resistance. So this resistance value is going to be very small, very, very small, right? And if we get a number that's approaching zero on the bottom of a fraction here, right, that all of a sudden skyrockets current up to infinity, right? And we get infinite current trying to be processed by this multimeter, and it can't happen, right? Our current multimeter can't handle infinite supplies of our ammeter can't handle infinite supplies of current. So it's just not going to happen. So we need that resistor there to modify or kind of moderate the flow of current through the circuit. Because the solenoid is not a resistor. A solenoid is just a piece of wire, right? And especially after its initial resistance to the current, right? Because if there's no current to begin with, when we first flick on the power supply, the solenoid will resist that change in current. But then almost immediately after, right, when that initial resistance goes away and the current's allowed to flow, we'll have infinite currents, or not infinite, but very, very high currents through this plain wire solenoid trying to pass through our multimeter, and our multimeter will shut down because it can't handle that. So we get a circuit with a resistance of zero. Right, we get a circuit that has essentially zero resistance if we look at V equals I times R. If R is zero, then V is zero and I is, or well, I guess it's easier to look at in terms of I equals V over R. If V is a set number and R is essentially zero, then I has to be essentially very, very much bigger than any reasonable number. So that is 17, number 3. All right, and I am going to really stop here because it's almost 11 o'clock. And I will catch you guys tomorrow. I'll try to do the other 3 tomorrow morning, hopefully. All right, so those will be available to you then. Catch you later.